All right. In this chapter, so far we have discussed some conversion rules on how to convert a physical model to the implementation in the particular DBMS. In particular, the conversion rules are aimed at converting an EER diagram into tables for implementation. But prior to implementation in a relational DBMS, it is necessary to ensure that the design of the database is not flawed. So the process of database normalization, which is introduced in this class, seeks to ensure that there's no significant data anomalies in the database design. In a sense, we are seeking to ensure that the tables in a database system conform to sound database design principles. Applications of rules describes the conversion rules of the ER model to tables. Well, if you apply these rules, in most cases, the resulting tables are already in the third normal form. Well, third normal form, which is a terminology that will be introduced in this class. But sometimes a few design flaws may still remain in the tables that result from mechanical application of the conversion rules. So, why do we need the database normalization process? Simply because that if the tables are not well designed, we will confront some data anomalies. So what is data anomaly? Well, there are three types of data anomalies we are concerned about. These three types are insert anomalies, delete anomalies, and update anomalies. An insert anomaly is the inability to insert or add data to the table because of design problems. A delete anomaly means that deleting certain data from the table inadvertently results in the loss of other related data which the user would like to maintain. And finally, update anomaly. An update anomaly simply means that a change in data must be performed in multiple locations rather than just one. And as you know, this is of course against the design of the database structure. System designers, not only the designers but also the users, they would obviously like to minimize the number of data anomalies in the relational database. Increasing levels of normal forms indicate that the tail conforms to stricter rules with consequently fewer data anomalies. In order to describe the process of database normalization, it is necessary to explain the concept of functional dependency. Let's assume in a table with two fields, x and y, if there's only one possible value of y for every value of x, then y is said to be functionally dependent on x. In simple terms, field x determines the value in y. Well, you're already aware of the concept of primary key and non-key attributes. The functional dependency notion simply means that all non-key attributes in the table are functionally dependent on the primary key. But it is possible for a table to have a functional dependency that doesn't originate from the primary key. So let's consider an example to explain this concept. For example, let's assume in a table containing data about the students, for every instance of the student ID number field, there would be exactly one name. In other words, the particular student will have only one name. So in this case, we can say that name is functionally dependent on student ID number. But it is possible that two or more students could have the same name. The name field doesn't uniquely determine the student ID field. So, although name is functionally dependent on student ID number field, the reverse is not true. We cannot say that student ID number is functionally dependent on name. Yeah, in other words, it works only one way in most cases. Well, now let's turn to an explanation of the three normal forms in the context of this example. A department in a business school would like to store information in a database about professor, their offices, and course taught by professors. Also, the department wants to keep track of the professor's teaching preference in terms of days and times. Obviously, the same course can be taught by different professors, and a professor can be teaching multiple courses. Well, if all of these attributes are to be stored in one table, or in other words, one relation, the results would appear like this, as printed on this slide. And as a reminder, in the following slides, the primary key in each table is underlined, and the foreign key are indicated with an asterisk at the end of the attributes. So this would be the resulting table. But obviously, this table is against the design principle of the first normal form. In Excel, if you keep this information in Excel, it can be realized. But if you keep information in a database, this is definitely against the design principle of database. Because first of all, this table is against the design principle of first normal form. So what is first normal form? So this relation is an example of non-normalized relation, since this table contains a repeating group. Simply stated, a repeating group appears in the table when there are multiple values at the intersection of certain rows and columns. For example, that table contains several instances of course number, description, credit hours, day preference, time preference. The existence of multiple cell value in one or more non-key attributes for a single primary key value is called repeating group. This repeating group prevents the table from being in the first normal form. A relation is said to be in the first normal form must have exactly one value in each cell. That is, a first normal form table has no repeating groups or no multiple cell values in non-key attributes for a single value in the primary key. So here's the solution. We can decompose that table into decompose one table into two tables, into professor table and course preference table. In professor table, in the first table, it contains information about the professor name, professor number, professor name, office number, and phone number attributes. And in the second table, course preference, it contains professor number, course number, description, credit hours, day preference, and time preference. Each of these two tables is in the first normal form because they do not have any repeating groups. And also, as will be discussed later, for professor table, which is the first table, is also in second normal form. So let's see the data anomalies appeared in the first normal form. I mean, you can consider the second table as an example to consider these three types of data anomalies: insert, update, and delete anomalies. Well, information about a new course offering cannot be added until a professor indicates a day and time preference of that course. It is not possible to add course information without professor information because the primary key in that table is a composite key of professor number and course number. So let me go back one slide. As you can see, if we want to add a course offering, it cannot be added until a professor is assigned to that course, and that professor indicates the day preference and time preference. So this inability to add data to the database is called insert anomaly. Well, that is, the users is unable to insert data into the database because of the bad design structure of that table. And this anomaly can be avoided by redesigning that table. Well, but how to redesign it? Let me explain this redesign a little bit later. Next, let's consider the problems associated with updating data in this table. If the description of a particular course is to be modified, that change will have to be performed multiple times rather than just once. Well, as you can see in this table, the course description for the same course is repeated multiple times. For example, AIS class appear twice, here and here. And also principles courses appear 2 times, here and here. Well, that means if you want to modify the description or credit hour information about these 2 courses, you have to modify the description and credit hours more than 1 time, which is definitely against the design principle of database system. Because ideally, the user should have to update the course description just once. for a particular course. This duplication of update effort is called an update anomaly. Update anomaly. And it is also avoidable by redesigning the table. Well, finally, let's consider the problems associated with deleting data. So let's assume that a particular course is taught by only one professor. If that professor leaves the university, like is fired or retired, if that professor leaves the university and his record is deleted from that database, we also lose information about the course that was being taught by that professor. But in fact, that course should not be deleted in the database system because that course offering is still alive in that department. So this inadvertent loss of data is called delete anomaly. And also, the delete anomaly can be also avoided by redesigning the database. To understand why these insert, update, and delete anomaly occur, let's consider the structure of let's consider the structure of this table in detail. The primary key, as I said, the primary key in this case, is a composite key, comprising both professor number and course number taken together. But the only fields that depend on both these two attributes are only day preference and time preference. These two non-key attributes are fully dependent on the composite primary key. For the other two non-key attributes, description and credit hour fields, all you need to know is course number information. So formally stated, description and credit hours are functionally dependent on course number alone, while time preference and day preference are functionally dependent on the composite key, professor number and course number. Since these two non-key attributes depend on only a part of the primary key, the problem is that they do not have an independent existence. So the anomalies described earlier result from this lack of independent existence of certain non-key attributes. Well, this is the introduction of first normal form. Next, I'm going to introduce second normal form. What is second normal form? The relation is said to be second normal form if first it is in first normal form, and second, the non-k attributes in the relation are functionally dependent on the entire primary key. So if you look at the professor table on the previous slides, I mean the first table on this slide, if you look at this table, the name, office number, and phone number fields are all functionally dependent on the professor number primary key. But as we discussed, course preference table is not in second normal form because some of the secondary key fields, such as description and credit hour, depend on only part of the primary key. So a solution to avoid the insert, update, delete anomalies for tables for table designs only in first normal form is still to decompose the course preference table into two tables. It is composed into two tables. Courses table containing information about course number, description, and credit hour. Another table, course preference table, contains the information only about the time preference, professor number, course number, and well, these two attributes are the composite key. In addition, we have day preference and time preference as non-key attributes. Well, as you can see, the course description and credit hours fields now have an independent existence since they are represented in the course table. Both the non-key fields in the course table, I mean the description and credit hour fields, they are functionally dependent on the primary key, course number. The preference table has two non-key attributes. Both of them dependent on the composite key. Taken together, professor number and course number. So we can say that in this case, the courses table and preference table are in second normal form. But as I said, professor table, I mean the first table on this slide, is only in second normal form, not in third normal form. So now let's consider the the insert, update, and delete anomalies in second normal form. We look at professor table as an example. Let's assume that there is exactly one phone in every office. So there can be only one phone number associated with a given office number. In a sense, what I'm saying is that the phone number non-key attributes is functionally dependent on office number non-key attributes. Well, this dependency between two non-key attributes is a relation that is called transitive dependency. Transitive dependency showing here. It means dependency between non-key attributes in a table. So put another way, any considered any functional dependency that doesn't originate from the primary key in that table is considered transitive dependency, which can potentially cause insert, update, and delete anomalies in the second normal form. But if phone number field refers to the professor's cell phone number, which would not change if the professor was moved to a different office, then there's no connection between the office number and the phone number. In that case, there's no transitive dependency in this table, and it would be in the third normal form. So it is essential to carefully examine the assumptions that govern the dependencies between fields in the table before conclusion can be drawn about conformance to second or third normal form. Okay, let's return to the assumption that an office can have only one phone number. The problem in this table stems from the fact that information about offices and phone number that doesn't have to be independent existence. Rather, this information is tied to information about professor. Let's consider the kinds of problems that lack of independent existence for office and phone information poses. First, it is not possible to add information about a new office and phone number until a professor is assigned to that office. So this is, as you know, it's called insert anomaly. Also, when a professor record is deleted, we also inadvertently lose office and phone number information about that office previously occupied by the professor who left the university. Well, that is, as you know, is delete anomaly. Well, the solution is also to further decompose the second normal form tables, such that all data that is independent of other data are stored separately. So let's look at third normal form. A relation is said to be in third normal form if first it is in second normal form. Second, all functional dependencies in the relation originate from the primary key. Or in other words, it means there are no transitive dependency in any relation. An additional requirement imposed from third normal form is the relation should not contain any derived fields. By definition, derived fields can be generated based on value either in the same table or in other tables. If derivable fields are physically stored in the table, and if the value from which the field is derived are changed without changing the derived fields, then in this case the database is left in an inconsistent state. Or in other words, if derivable fields are stored, then they would have to be meticulously updated every time when there's a change in the value of underlying fields that make up the derived fields. So, to avoid such potential inconsistency in the database, the third normal form required is sometimes extended to include the constraint that database not contain any derived fields. So back to our example. In one word, we can say that to resolve these problems, I mean the insert, delete, insert, update, and delete data anomalies. Our solution is only to decompose the table, to separate one table into two or more smaller tables that contain less attributes. For example, let's go back and see our original table design. In order to avoid the data anomaly problems, we can now decompose this table into 6 tables. These 6 tables are professor information table, office table, I mean 4 tables: professor information table, office table, courses table, and time preference table. So here is the summary of the normal forms. In first normal form, there are no repeating groups. In second normal form, no fields depends on only part of the composite's primary key. Or in other words, in second normal form, no partial dependency. And the table is in third normal form when there's no derived fields or no transitive dependency. But it may be sometimes acceptable to violate third normal form in some instances, so long as you realize what is lost by non-conformance to the third normal form. In this example, the professor second normal form table with the fields professor number, name, office number, and phone number may be left only in second normal form if it is not considered critical to keep track of offices and phone numbers in offices. So, the insert and delete anomalies outlined for the second normal form professor table may be deemed acceptable in this case, and the organization may decide to leave the table may decide to leave that table, I mean the professor table, in second normal form. It is important to realize that the normalization rules are merely guidelines, and common sense would prevail in database design. As you consider the consequences of violating any of these normal forms, you should think in terms of anomalies that result from such violations. You should consider what are the insert, updates, and delete anomalies that result from such violation. If these anomalies are undesirable, then the normalization violations should be corrected. The process of database normalization can be mastered only by participating normalization techniques on sample and real-world problems. So, well, I think that's all of this class. And in the next class, which is the last class of this in this semester, we will introduce the implementation of designed relational database system within Microsoft Access. Actually, this part is kind of out of the description, I mean the guideline of this course, but I still want to introduce this last step to you. So I will see you again. I will see you on this Wednesday. Before I leave, please let me know if you have any questions. Any other questions? No? All right, so I will see you guys on this Wednesday. See you.